Today, implicit differentiation. Implicit differentiation. This, by the way, is section 3.7 in your book, chapter 3, section 7. All right. So here's what I'm going to start with. Find the slope of the tangent to the circle, x squared plus y squared equals 16, at x equals 2 in the first quadrant. All right, so here's a nice picture of it. Be aware that this is the equation for a circle. The equation for a circle is x squared plus y squared equals r squared. That's a circle centered at the origin. Of course, if you want a circle centered off the origin, you put a minus h and a minus k with the x and y respectively. And what you have over here is r squared. So this is the square of the radius. The radius of the circle is 16. So, the r squared is 16, so the radius is 4. So this is a circle of radius 4 in the first quadrant. Okay, so you should start by saying, okay, how would I do that? Try and think about it, see if you can do it. Pause the video, see what you can come up with. Okay, having paused the video and thought about it and coming back, hopefully one of the things that you thought of is if I want the equation of the tangent, then I need dy dx, and I can't get dy dx until I get the y by itself. So the first thing I need to do is actually solve for y here. So then y squared equals 16 minus x squared. Y equals plus or minus square root of 16 minus x squared. It'll be really useful if you're aware, like just have in the back of your mind all the time, that this is the equation of a circle solved for y. All right, now we're going to take advantage of the fact that we said in the first quadrant, because notice in the circle radius 2, there's 2 points where x equals 2. One in the first quadrant, one in the fourth quadrant, okay? But we're looking for the first quadrant. That means we want the positive part of the circle where the y is positive, so we're going to choose the positive because it's first quadrant. Okay, so we're really looking at the equation y equals square root 16 minus x squared, also known as 16 minus x squared to the 1/2 power. All right, so if you didn't think of solving for y, then you should pause now and say, okay, what's my next step? Find the derivative. So find the derivative next. Okay, so hopefully you've had a chance to find the derivative, dy dx. So dy dx equals, all right, so this is a chain rule. So you have an inside function and an outside function. We're going to keep this inside function the same, do the derivative of the outside function. The outside function is a power rule. Bring out the 1/2. Keep the inside function the same, 16 minus x squared, right? Keeping that inside function the same. And subtract 1 from the exponents, we have the negative 1/2 power. Right, then I have to do times the derivative of the inside function times g prime, which in this case is negative 2x. Right, the derivative of 16 minus x squared is negative 2x. So we have that, which we could rewrite if we want algebraically to be a negative 2 over the square root of 16 minus x squared. All right, and that's the derivative of, that's dy dx for this circle, for the top half of the circle. This is the bottom half of the circle, is just going to have positive there. Does that look right? Yeah, it looks right to me. All right, so now if I want to know the slope of the tangent, all right, we don't want the equation of the tangent, we want the slope of the tangent. That means all I need is dy dx at that particular point. So dy dx evaluated at x equals 2 is going to be negative 2 over square root of 16 minus 4, because 2 squared is 4. So that's negative 2 over square root 12. Now you do your geometry, radical simplification-y stuff. So we're going to have negative 2 over 2 square root 3. So that equals negative 1 over square root 3, and that equals negative square root 3 over 3. All right, so that's the slope of the tangent line. Now, of course, I asked you that question, I ask you this one. Is there an easier way to get the derivative when we're in this situation that we had to solve for y, and the fact of solving for y took something that would be really easy to deal with and turned it into something very messy to deal with? Is there a way to get around that? Yes, there is. It's called implicit differentiation, and that's what we're going to learn today. All right, but first I want to notice something else, by the way. This is method 1. This is using the calculus that you've already learned. All right, so here's a method 2. Let's make that green. Method 2. So this is using geometry. Did anybody think to use geometry on this? You can solve this without using any calculus at all, you know. It goes like this. Make a nice triangle here. since the radius of the circle is 4, this is 4 right there. Since this is 2 and this is 4, that means the hypotenuse of a right triangle is twice the shorter leg. That makes this a 30, 60, 90 triangle. All right, so that means we know that this is 60 degrees right there. So we know that this is pi over 3 radians. All right, and so now we know the slope of this. I mean, you can do it different ways. You can say the slope of this segment is the tangent of pi over 3. All right, so the slope of the radius, all right, slope of the radius is equal to tangent of pi over 3, which is square root 3, right, because it's tangent of pi over 3. And then the slope of the tangent, so if you remember from geometry, a tangent is always perpendicular to the radius. So you can use the opposite reciprocal. All right, so the geometry method is much easier. However, it only works for x equals 2, you know, and maybe a couple other values. So if you had x equals 2.5, geometry method does not work. And then you have to use calculus. So we'd also like an easier calculus method. So we could, you could have x equals 3, even x equals 3. You might be able to do, no, I don't think so. If you had x equals 3, geometry is not going to help you. So you would have to do calculus. So I'm going to show you an easier way to do it using calculus. That is our next video.